Okay, a resistance force. Good. So let's just define friction to be a resistive force that occurs when two surfaces are in contact with each other. Two surfaces have to be in contact with each other to have friction. And so the reasoning for this, well, if you were to look at two surfaces, they might look smooth. Like, so if I take this book with this lab station, you look at the book and the lab station, they both look like they're really smooth, right? However, if you looked at them with a microscope, how are they going to look? Very different. You remember in biology days, things under a microscope look very different. And so that's what would happen here is maybe the book surface looks something like this. Maybe the lab station surface looks something like that. And so as these two try to slide by each other, this is like a microscopic view. So as these two surfaces try to slide by each other, well, the grooves are, it's going to get kind of caught up in these grooves, right? For example, let's just do a little demo with ourselves. So if you take your knuckles, take your fist, right? Let's make a fist. And if you try to slide your fist by each other, you feel that resistance as you try to move your fist by each other. You can feel the knuckles bumping in, it's getting kind of caught in the grooves. Same thing happens when a book slides across the table or anything slides. It's going to get caught in those grooves and it slows it down. That's friction. That's the resistive force. Okay? And what would happen if I put oil on the surface? Okay, friction decreases. Now why does it decrease? It kind of like fills in these little gaps, right? If you put oil on the surface, fills in the gaps, and you're essentially smoothing out that surface, right? And then you're going to reduce the friction. They're not going to get caught as easy within those grooves. Okay, so that's going to be our friction force. There really are two main factors that affect friction. And you have definite concept on one of these and somewhat on the other. What's one factor that affects it? The acceleration actually doesn't directly affect how much friction there is. The mass and the surface roughness. One of those is definitely correct and one of those is partially correct. So let's talk about the roughness. Is roughness a factor with friction? Yes, okay, obviously yes, you did a whole lab on it. So one of the factors is the surface roughness, and even just conceptually, I mean, you can visualize, like, if you go running and sliding on ice, it's going to be a lot smoother than if you go running and sliding on sandpaper, right? So the surface roughness is going to be more. And it is between both surfaces. So ice on ice is going to be smoother than ice on sandpaper. And that's going to be smoother than sandpaper on sandpaper, right? So it's between both surfaces. That's important. The way we characterize the surface roughness is something we call the coefficient of friction. Basically, this is just a measurement of the roughness. So the higher, the more rough a surface, the larger the coefficient will be. The smoother, the smaller. The symbol we use for this is a Greek letter. Looks like this. Anyone know the name of that Greek letter? Mu. Good. So this is called mu. Okay, mu. Looks like a script U. The little tail in the front. Okay, the higher the mu, the higher the coefficient, the rougher the surface. Now these will usually be kind of small, typically under 2, maybe more typically under 1. So they'll typically be real small numbers. All right, number 2, so someone said mass. Yeah.
Surface area of the surface is...
Believe it or not, the surface area actually is not a factor. Yeah, it's not a factor that affects the amount of friction. Yeah.
Because mu increases and the surface area the surface roughness increases.
Yeah, exactly. As mu goes up, roughness increases. Okay, the other factor is essentially, yeah?
Weight.
Okay, you're
Force of gravity.
close with weight. You're close with weight. Very close. And let me just let you know, tell you what it is, and then we'll talk about how weight is kind of a factor. So number 2 is how hard the surfaces push against each other. Push against. How hard the two surfaces push against each other. So let's go back to our little demo. You can see this. So if we take our fists, take our knuckles, right? If you just kind of barely touch them and slide, pretty easy to do, right? Not too hard. Now try to push them as hard as you can. And now try to slide. Okay, what happens? Okay, hard, right? It's much harder, maybe painful somewhat. That's what happens. That's two surfaces pushing hard. The harder they push, the more friction there'll end up being, the more resistance. Okay, so let's look at this. So we actually have a definition for how hard surfaces push against each other. What do we call that? Okay, that is called the normal force. That's called the normal force. Okay, so going back to the concept of weight, in the lab you should have saw this, that if we take an object, let's say this is 100 newtons, it's pushing down with 100, well how hard is the table pushing back up? 100 newtons, right? And if I put a 50 newton object on top of it, now how hard is the table pushing? 150, right? So the more push down, the more push up. Now that's indirectly related to the weight. And in the examples I just gave you, it's exactly the weight. However, what if I push down with another 100? Then what happens to the normal force? Then it increases and there's going to be more friction. The weight was still the same, but the push down now is all of a sudden greater. So the friction itself is directly proportional to how much pushback there is from the normal force. Okay, and a lot of times that will be equal to the weight. It's definitely going to be related to the weight in most cases. So let's just derive the equation for friction. Should be pretty straightforward. Force of friction is equal to, well, if a surface is rougher, what happens to the friction? Increases, right? That's a nice direct relationship. So if mu doubles, what happens to friction? Doubles. If the normal force increases, what should happen to friction? Should also increase. It's directly proportional as well, so as the normal force doubles, the force of friction will also double. So here's our equation for friction. Simply mu times normal. Okay, those are the two factors. Yeah, go.
You didn't give us all these equations like that.
All these? You mean this one? Yes. I'll give you F net equals MA, and
Yeah,
I'll give you
that's
this one. Yeah, but I'm not going to give you all of these summations. No, you have to derive the summations, because I mean there's literally hundreds of scenarios that we could think of, and I'm not going to give you 100 equations. Yeah.
Can you say that thing that you said about normal force one more time, please? Where you said, like, if you were pushing the book down with 100, and then you said something about 50, and it equals 150, but I didn't get it.
Oh, so in this example, we have the book is 100, Fufar is 50. So together, the table now has to push up with how much force? 150, right? And if I push down with another 100, now how much does the table have to push up with? 250, right?
So that's what the
Normal force is how hard the table pushes back up. Yep. So the more force pushing, it's a reactive force. The more force you push down, the more force it has to push back up. Okay, last little thing with friction, then we'll do one example. There are two types of friction, or two types that we're going to talk about. And probably by the name, you could figure out the meaning of these two types. So first type is called static. And the second type is called kinetic. So what does the word static mean? Stationary, not moving, right? What does the word kinetic mean? Okay, moving, okay, motion. Remember kinematics, okay, it's all about motion. Kinetic has to do with motion. So anyways, kinetic, let's just define this one first. So this would be friction when an object is sliding on a surface. And then kinetic would be when it's not. Okay, when it's not sliding. It's the best way. It's the opposite. So friction is, I'm just going to use the word stationary. Now that does not necessarily mean not moving. So it's not like if something's moving, it's kinetic, and if it's not moving, it's static, although that is often true. So let me just give you a visual of this. So here's our book, right? I'm going to push on the book. I'm pushing the book, but the book's not moving. Why isn't the book moving? There's too much friction that keeps it from moving, right? Well, what's keeping it from moving? Static friction. So there's too much static friction to enable this to move, right? If I push enough, though, if I push harder, eventually I can get it to start moving. Now, once it does start sliding, then what kind of friction is it at that point? Kinetic friction. So static is before it's moving. Kinetic is now once it is moving. That's called kinetic. Yeah, if that helps you remember it, that's a good way to do it. Definitely with the kinetic case, it works. Let me give you another example, though. So this is an example of something that's moving, but it's actually a static case. So for example, if you're driving in a car, let's use an example of like a pickup truck. If you're in like the back cab of a pickup truck, or this case with Bufar on this car, I can move this car right now, right? The car is moving, and Bufar is moving too. Now, why is Bufar moving? Okay, there's actually no seat. There's no seat pushing him. What's the thing that's pushing him? And I'm not touching him. So what's the thing that's actually pushing him? The static between him and the bottom here, the seat, right? So the static between him and the seat, that's the thing that's actually moving him. So that would be static friction, even though he's in motion, because the static in this case is actually moving. Now if he's moving and he hits a wall, what happens? Then he starts to slide forward. And once he slides on that surface, then what kind of friction is that? That would be kinetic friction. So once he starts sliding, okay, we would consider that kinetic. Okay? All right, so that's static and kinetic. Anyway, from a formula standpoint, the only way we really differentiate these is we'll say there's a mu sub s, and we'll say there's a mu sub k. Static coefficient, kinetic coefficient. Do you think these are the same numbers? Do you think static's greater than kinetic? Kinetic greater than static? Or sometimes, who knows, sometimes one's greater, sometimes the other's greater. Yeah. Think back to the lab that you did when you were pulling on the little blocks. Was it easier to get it started, or was it easier to move it once it was moving? Once it was moving, it was easier, right? It was easier. So therefore, let me say the question again. In which case is there more friction, static or kinetic? Static. So it took more force to get it moving than it did once it was in motion. Okay? All right, I think it's time to do a problem.